Okay. Yep. Wait. Sorry. Okay. Can I just get your attention, please? So, yep. My friends over at CEVSOC, they're hosting the Women in Civil networking night, and these girls, Pragya and Sarah, they can tell you a little bit more about that. So, yeah.
Hi everyone, my name is Pragya, and this is Sarah. We're part of CEVSOC, and we're about to host a Women in Civil networking night, in which we've invited some really successful, inspiring women from the civil industry, and they will be talking about their experiences in the industry, any things that they have, like experiences that they felt, and if you want to get to know more about them and their experiences and you have any questions, you want to network with perhaps other women or just get to know things about civil industry, like the actual industry, because we're like university students, so we're seeing it from like a bubble on the outside. So if you want to get to know more about the inside, you should consider attending this event. It's on the 26th of June, Wednesday, 6 to 8 p.m. Tickets are now on sale.
Yep. So we got our ticket registration link. Tickets are only $7, so we really encourage you to come along. Have a good time networking. There's going to be free food as well. Even if you're not in civil, it's just a good chance to kind of network with big engineering companies. The engineering companies after us are like Oricon, Ward, Langer, which is the head office that we'll be heading up to. It's just a really good opportunity to get to know some of the professionals that are in the field and have a good time at network. So yeah.
And you don't have to be like the women for fun, but you can just support, like, yeah, and it's in Wall City. I hope we see many of your faces there.
Yeah, it's open to pretty much everyone.
Yeah, and dinner's included in the ticket pricing, so it's a pretty good deal. Yeah, good bang for your buck. All right, thank you. All right, guys, so without further ado, once I get this working, I think that works now. All right, so what I'll do is I'll pull up the QR codes and stuff first. One second. So, just the admin stuff out of the way first. The bottom left is the attendance form, so you can give that a scan and sign in for this week. The bottom right is my notes. So again, I like to go a little bit quickly sometimes. If I scroll past what you're writing, you can always just refer back to this. I've got the work in progress document for workshop 3 up there right now. That's what I'm going off of, but more often than not, I'll make a little mistake and try to fix it up. So that's why I call it work in progress. When that work in progress part is off the name, then you'll know that's like the finalized kind of document. In terms of our lesson plan, at the start, it says the quizzes is first, but I'm just going to change that real quick. We'll do the quiz after I go through the theory. So I'm still scanning that? Yep. So this week we're going to go through distributed loads and methods for solving beams. The focus of this week will be beams. And then we're going to go through some questions as well. I'll teach you guys 2 methods on how to solve beams. One I like to call the graphical method, one I like to call the algebraic method. I'm not sure if these formally have a name, but yeah, I'll go through that in a bit more detail. And as well as at the very end of this week, I'll also include some machines and frames, explain what those are in the context of this course and how this course is taught in other schools as well. Okay, has everyone got the QR stuff? Scan? At the bottom here as well, I have the recordings. They're found on YouTube, but you can go back and see the previous weeks of these recordings week by week. So if you ever miss it, you can refer back to that. Or later in the course, if you forget stuff, you can always go back. Okay. So, in terms of our little tree diagram of the progress of where we're up to in this course, so I showed this the last 2 lessons as well. We're still in statics, right? Statics will be the first half of our course. And now we're getting more into the actual structures that are specific to civil engineering and structural design and stuff like that. So we're going to be talking about beams extensively this week, and next week we'll be focused on trusses. Assuming the course hasn't changed, then you guys have seen that in the lecture as well. Yep, and I'll briefly touch on frames, but you won't be assessed on frames, I believe, until later in the course. But yeah, again, the focus will be on beams. Interestingly, in the mech school, they teach trusses before beams, but in the civil school, they teach beams first. They're both difficult in their own way, but for different reasons, so you'll see that. Okay, so internal forces in a beam. So basically, with Newton's third law, the free body diagram law essentially, you can slice the analysis of a beam, like you can slice where you're analyzing a system such that it crosses over the middle of a beam. And when you expose what's inside a beam, you'll see that there has to be a counterbalancing force for the external loads. These are called the internal forces in a beam. And there's three kinds of actions that they have to counteract. V stands for your shear force. Shear forces are like perpendicular loads, loads which are perpendicular to the beam. And if you remember, we said that a beam is kind of like, it has this axis, right? This axis kind of goes through the beam, running through like that. So these are the kind of perpendicular loads. N is our axial loads. So we've talked about tension, compression, those are axial loads. And those will be represented using N. And lastly, we have the internal bending moment, right? Internal moment, right? And what's important is that we have a left-hand side and a right-hand side convention, because when we plot out what we call the shear force diagrams and bending moment diagrams for beams, you kind of have to graph along the beam, either going from left to right or right to left in order for it to work out, right? And generally, I like to stick with left-hand side convention, but you'll see in one of the questions which I've shown below, it's advantageous sometimes to go right to left instead. Okay. Essentially, we're just using the tools which we've been kind of talking about last few weeks to solve these. So that's the equations of equilibrium. Equations of equilibrium. So we can literally just use these ones. Let me just move a few things around real quick. Essentially, you'll see this properly in the question, but you use the sum of the vertical forces is equal to 0 to solve for your shear force, right? If we're analyzing, so if we take our free body diagram cut and expose the internal forces, those will be part of the forces we have to consider when we're looking at all of the vertical forces, right? And and then we'll be solving for V, which will be the shear one. And then for the axial forces, we'll be solving for N using sum of the forces in the X direction. And the sum of the moments, sum of the moments around the cut for M. So, by the way, this action, our internal bending moment, it's happening about where the cut is. This will make more sense when we see it in practice in the question. But just keep in mind, even if I draw the counterclockwise arrow going like there, we're referring to this point here, which is exactly at the cut. Okay, does anyone have any questions? If you do have some questions, they might be answered as I explain the next few things, right? So next, is anyone still copying that? If you are, you can go back to the Google Drive stuff as well. Okay, actually I might just focus on this. So I think last week I briefly talked about distributed loads. I've talked about how I like to draw my distributed loads, or uniformly distributed loads with the little curvy lines, I guess. That's just the lazy notation. Formally it looks like this, and usually you denote it with a W that just represents some sort of distributed load, and the units are in kilonewtons per meter run of the beam, so along the span of the beam. The middle, okay, so if we make a resultant force from all of the distributed loads, right, it's because we kind of can visualize it like a rectangle, it's going to be in the middle of the rectangle, right? So when I say a rectangle, what I'm talking about is this kind of like along the beam axis multiplied by the verticalness is like the magnitude. That area represents what the resultant force would be, right? And the location for that resultant force is halfway along our distributed load, like in the middle. It's kind of like center of mass, but center of force almost, right? Does that make sense? So that's the simplest case. That's called a uniformly distributed load, sometimes denoted as UDL. If we get a bit more complicated, we have our triangularly distributed loads, right? And we have two types. So there's linearly increasing loads and linearly decreasing loads. Usually you don't have to be super technical with explaining these, but you just need to know that they're kind of like these. There are two types of triangularly distributed loads, right? And so on one end, it's always, if it's a triangle, the magnitude is always 0, right? So in the linearly increasing case, it starts at 0 if you're going left to right. And in the linearly decreasing case, it ends on 0 if you're going left to right, right? And the other one, we call this W max because W, it can be graphed. It's like a function. It's like in high school you have like it's x, y, you can graph it on a Cartesian plane, that kind of thing. But we just replace this with W on the y-axis, and x is still kind of denoting how far along the beam you're going, right? Okay. The idea is for a triangle, right? Center of the center of force, right? It's 2/3 along the beam from the small side, right? That's what I said here. 2/3 along from the small side, or 1/3 along from the big side, right? Just you're gonna have to get familiar with that relationship. But again, so just for a triangle, it's always 2/3 from the small side or 1/3 from the big side is where the resultant force will be. How do we get the area of this resultant force? Well, if we view the previous one like a rectangle, we can view this one like a triangle, right? So in order to get R, right, which is our resultant force, you multiply this axis by this axis and divide it by 2. Area of a triangle, base times height divided by 2, right? Simple as. So that, when you get the area, that's going to be what R is, and then the location of where that R point load is what I said earlier. So I don't know how many questions so far. Okay. So we get a bit more complicated when we're dealing with trapezoidally distributed loads, right? You can imagine we're just getting a bit more complicated. It's still linearly increasing, so we have our linearly increasing load, or linearly decreasing, right? So that's the decreasing case. Now, instead of one side equaling 0, we have a minimum and a maximum for what the distributed load value magnitude can be, right? Makes sense so far? Okay. So, oftentimes, and we might see this later in one of the questions, you can actually just divide these up into a triangle and a rectangle. That would be the way that I do it to avoid doing unnecessary integration in calculus. So the idea is that there's this principle of superposition in statics, which says that this trapezoid is the same thing as if you stacked a rectangle on top of a triangle, right? And so the resultant loads would be in the middle for the rectangle, and that magnitude of that rectangle, and 2/3 along from the small side for the triangle. So that's that one there. You can call that R1, R2, and you can do your calcs from there, but this case is fairly rare. I would kind of doubt that you get it, at least for your week 5 midterm. It's possible to get in the finals kind of scenario, I would say. Okay. I should probably also mention while people are copying stuff down that next week you have your labs. Is that right? I think there's 4 lab demonstrators. I'm one of them, so you might randomly get in my class. It's a really simple lab. Generally, it's like way the lecture is really nice. Like basically the lab demos are free marks. Like the lab stuff, it's all free marks. You just need to learn how to use this program called Space Gas. And for those of you who have done DESN 1000 with Way as well, for the structural stream, yeah, you use the same program. It's very easy. It's pretty much the same every year. And so, yeah, it's free marks for doing questions using Space Gas. Cool. Okay, so here's like basically in the civil school, you're not going to get this on an exam and you're not going to get this on a midterm, but I just want to like let you know like the derivation a little bit, and yeah, so the idea is that not in problems, but like in reality, a lot of distributed loads might not actually be uniform. Like we do make a lot of assumptions to simplify it to make it easier for ourselves, but in reality, you could have some areas with higher loading than others, etc. Right? So here's like a non-linear kind of varying load that you can see here. And when I was talking about graphing, right, you can bring out all of your high school graphing skills from maths, and there's functions that you can create, functions of w with respect to x. You have your initial value. If you're going left to right, you call it wo, and then this can be a polynomial, all these things. You can basically graph it. You can graph what this line is, right, for what this distributed load is. And in order to get the magnitude of the distributed loads, you take the integral of this function with respect to x, and you get the area underneath, right? That's essentially what the magnitude is of that distributed load. Yeah, it's what this resultant force would be. And a step further, you can actually find where the location of this distributed load is along the beam. It's called a centroid. And so you follow this formula. It's the integral of x multiplied by this function with respect to x, and then dividing it by r. So r is this one. So if I wanted to draw this out fully, it would be this. Yeah. It's a similar derivation to center of mass. So center of mass would be, sorry, my bad. Center of mass, let's say in the x direction, would be mass, sum of the mass times x, the sum of the mass. Something like that, right? What we're doing is we're multiplying it by x to find that location of the center of mass. I think I'm overcooking this explanation a little bit, but yeah. This is just where it comes from. You don't need to memorize these integration formulas, etc., right? But yeah, hopefully everyone understands distributed loads now, right? Because we're going to need a pretty good understanding of it when we learn our methods for how to graph bending moment diagrams and shear force diagrams and things like that, right? Okay, I'm just trying to think about my quiz. I think I'll run through this bit of theory and then I'll give you the quiz, because I'm not sure if this kind of theory is in my quiz, so I'll just be safe and go through this as well. So essentially there's two ways that you can solve bending moment diagrams, shear force diagrams, which I've been alluding to, right? First of all, for beams, you always solve for the support reactions. You use equations of equilibrium, which we ran through last week, and that's actually only the first step in this bigger problem. So all the content that we learned last week, that's just building up for this topic and the trust topic for next week, right? Next, we can choose to use one of two methods, right? And one is called the graphical method, right? And there's going to be advantages and disadvantages of both. So for the graphical method, it's actually faster. It's easier conceptually to understand. So it's actually going to be the one that I'm going to teach you first, right? But it has limitations, right? Because it can't solve every type of question, right? It can only solve questions with point loads and uniformly distributed loads. So you have to be careful of what your external loads are, and then you can see whether you can jump straight into the graphical method or not. Otherwise, you have to use the slower method, right? Which is the algebraic method. It's also harder to conceptually understand. Like when I go through my explanation, I'm going to spend more time going through how this one works, I believe. But the good news is you can solve anything with this topic, within the beams topic, beams related, right? Using this method. Okay, so I'll go back to this later, but what I'm going to do is I'll give you the quiz now, and we'll run through that. Yep. So if you scan this, just quiz you on what I've been talking about. Yep. Also, while I would love to finish this class early, like we've been doing the last 2 weeks, I think realistically it's gonna have to run on time. So, because there's a lot of content this week, and there'll be a lot of content next week as well. It'll be more than we've been having the last 2 weeks. All right, is anyone still scanning that? If not, I'm gonna get started. Okay, I'm just gonna get started now. Good luck. Just connected my headphone. Okay, we'll go on for another 10 seconds maybe. All right, 5 seconds. 5, 4, 3, 2, 1. Sorry, I'm gonna end it early. You guys are still going. Oops. All right, good luck. I mean, good job to these people. Very good. All right, let's review the questions. So it looks like we're still getting good at this part in the term. Okay, which type of these loads are not distributed loads? So for those of you who said point load, very good. So there's no such thing as a point distributed load. So you can either have a distributed load or a point load. They're separate concepts. So UDLs are your uniformly distributed loads. That's just a shorter way of saying the rectangular kind of load, right? So which of these two diagrams are interlinked? Oh yes, I straight up didn't tell you guys what this meant. So basically, the idea. Okay, kinetic moment diagram is not a thing. So the idea is that. Okay, let's bring this over to Discord. Basically, right. If you have some sort of setup like this, right? And you have a diagonal point load, right? On your simply supported beam, let's say. So there's basically going to be some sort of compression force from like acting on this part of the beam due to that horizontal loading, right? And there's also going to be some degree of shear force. So shear force is the perpendicular portion of the loads, right? And these reactions will kind of work this way, right? Yeah. So for the shear force diagram, jumping ahead. Okay. Just for now, trust me, bro. Like those two are interlinked. The shear force diagram and the bending moment diagram, and it's easier to show you why once you actually get to the questions. I can't think of a good example off the top of my head. Okay, so yeah, I was talking about the non-linear varying distributed loads. So that's like the curvy line one, or it can be whatever shape, right? The magnitude is just the area of it, essentially, right? And the centroid is, yeah, that formula I drew up before, but it says the integral of x times distributed load multiplied by the magnitude. Essentially, we need these shear force diagrams and bending moment diagrams to design beams properly. It's actually, yeah, it's one of the most foundational skills for structural engineering you're going to find. So, yeah, you'll see in the rest of your degree, it comes up a lot. So it's really good to practice these skills because when you practice them, it will make it so much easier for your future courses. Okay, I'll give you guys a break for now. Yeah, so we'll come back at 4:40. Yeah, let's go early break.
I don't know. It's due on Tuesday, That's fair. What's up? Yeah. Oh, well, I don't. Right.
Okay. All right. Just continuing. So I just want to show you something because I remember getting asked about this at the end of last class. So there's a pretty good thought process which someone was talking about, which is that what if that force it landed on the surface there, and so you use that radius to figure out the geometry, right? Which would kind of make a lot of sense. I think it's a contact force rather than a body force, but I'll just show you the answers here. They consider it in the middle. Yeah. Yeah. I didn't do engineering studies actually, but you're probably right, like in high school. But yeah. If that's a thing, you can look it up and have fun researching that. But yeah, it's something to do with law of transmissibility then. Good point, yes. Okay. So just continuing on with the rest of this class, I guess. So just on the board, I've briefly written out kind of like the steps in your head you're going through and ticking off to learn the content. So I forgot my markers today, so I'm using the ones from this room, and they're like pretty shit. So the first one says, you need to know what a beam is, right? Which I realized I maybe didn't fully explain properly, so maybe we'll go over that. And then you need to know what the internal forces are, you know. well, that's what I was talking about. When you cut a beam through with your free body diagram, section cut, you can expose those internal forces and see what kind of stresses are acting on the beam, right? And then you need to learn the graphical method, which I'll teach you first in the first few questions, and then we'll move on to the algebraic method as well. So, maybe we'll talk about what a beam is. That'll probably help. So basically, in a structure, right, this is a frame, right? It consists of a bunch of different structural members. I've just drawn it in perspective view and 3D, all that. So beams are the horizontal members, generally, and they generally take gravity loads perpendicularly, right? So if you imagine the loading, they're designed to resist these kind of perpendicular loads, and you'll see in solid mechanics that the shape of these beams and the geometry and material selection and everything, they're optimized to resist these kind of perpendicular loads, because that's the main actions which will be acting on it, right? That's what we're going to be analyzing. So I should probably just clarify that firstly. So the horizontal members, generally there's not much reason for beams to not be horizontal. So yeah. Perpendicular to the direction of gravity, basically, right? Okay. So here's a beam, for example. So in engineering mechanics, they're just going to chuck a bunch of beams at you that might not be super realistic, but they're like little puzzles, just like mathematically and hypothetically, what would everything look like if we analyzed it with this scenario, etc. Right? Okay, so what I've done is here's what our beam looks like, right? And just right off the bat, you can see that this, like, does anyone want to guess what that is?
Roller support.
That's a roller support. So it's a little different from the one that you might have seen that looks like that, right? They can come in a bunch of different shapes and sizes, but essentially they do the same thing as that one, right? So it's supposed to be there to resist just the normal forces, right? Whereas the pin support is for normal forces and tangential forces, right? And we also have our point moment, which you'll see how that interacts with our diagram. So do you remember last lesson, we had that question towards the end, which had that point moment. And someone asked, well, does it matter where a point moment goes in on a structure? Because will it just affect the structure the same amount, like regardless of where it's placed? And you'll see that when we graph the bending moments, it will matter the position of where it is. Another thing to note is that everything is in mil right now. So what I've done is I've converted it into meters. Just makes it a little cleaner if we're working with everything in the same set of units. So the set of units that I'm using, kilonewtons, meters, and kilonewton meters. Also, kilonewton meters is not the same as kilonewtons per meter. So distributed loads are the ones that will use these ones, right? Kilonewtons per meter. Moments are the ones that are going to use kilonewtons multiplied by meters, right? Okay, just keep that in mind. Okay. So we need to, wait, let me just quickly pull up my notes because I'm trying to see how much this question actually needed to do. Okay. Yeah, okay. Basically, it asks us to construct shear force and bending moment diagrams as well as find what the value of bending moment is at B. So this is like, what are the internal bending moments at that specific point? And with all of our graphs and stuff, we should be able to just locate that along the graph and say what it is. Okay, so I'm going to go through this relatively slowly because it's a new method. Well, actually, firstly, I'll go through one part quite quickly, which is finding the reactions, right? So just a little recap from last time. We're looking for these unknowns, right? And I'm going to outline where the lines of actions of them are, right? And so can someone tell me where you could take possible locations to take the sum of the moments about? There's exactly 2 spots which will work. You take it about B and A, yeah. So if you take it about B, if you take the sum of the moments about B, it eliminates these unknowns because the lever arms to them will be 0. and then you can solve for AY. And if you take it about take it about A, you can do the same thing and solve for BY, right? Very good. Okay, so let's start by doing that. I'm going to take the moments about A. Right. So we have to account for this, I'm going to account for this point moment first, right? So that's straight up just going to be 1.6, right? It's going counterclockwise, so that's going to be added on, right? And then BY, that's this one, is going to cause a positive moment about A. So it's going to be positive. Its lever arm is 1 meter because 0.5 plus 0.5 meters is 1. Right. And lastly, we have to account for this point load 2, right? The point load 2 is going to cause a clockwise spin about A, and so it's going to be minus 2 times the lever arm, which is 1.5. 3 lots of 0.5, right? So we can rearrange for BY, and we get 1.4 kilonewtons, right? Okay. We can also take the sum of the forces in the horizontal direction, right? And we only have one thing acting that way, which is AX, right? So that one's quite straightforward. That one's just 0. Right? Okay. And we take the sum of the forces in the y direction, right? And now we have to account for, we know BY, and we have to account for not that. We have to account for these, right? So for the sum of the forces, we don't take into account point moments, okay? Going to replace this with what we solved for over here, which is 1.4. And we get that AY is 0.6 kilonewtons again. So now we've done the first step, which is solving for reactions, right? That's the first step when you're solving a beam. Okay, the next step, and what we're going to spend a bit more time talking about, is shear force diagram and bending moment diagram. So these two concepts that are related because we care about the perpendicular loads for the bending moment, right? We care about the perpendicular loads acting on the structure, right? And how they cause bending. Okay. So let's focus on the shear force diagram first. So you graph it like you would in high school maths or something for the x and y plane, and on the y-axis we're going to be graphing V. So what I've done is, how I like to do it is, this is called a free body diagram, right? What I've simplified our little schematic of the structure to be. I've drawn it here, and the good way, like, how to say this, like, it's a good habit, basically, right, to draw the shear force diagram and bending moment diagram right underneath the free body diagram. Do you see how it lines up vertically? The reason for that is you don't need to double up on drawing your geometry, so it saves you time. So this leftmost point represents the leftmost point on the shear force diagram. Do you know what I mean? And we're going to be doing things left to right. So essentially, are you guys familiar with piecewise functions? In the algebraic method, you'll see the breakdown of how we're going to construct essentially a piecewise function for the entire beam, right? So what that means is, in maths, you have like the functions, and then it has like this thing, and then this for x is whatever between these amounts and between these amounts and between these amounts. We're constructing that, but in the graphical method, we speed up that process because we don't need to do all of those, we don't need to find all those functions quite yet. Okay, so what we do in the graphical method, here's the rule. So when you have a support reaction which is positive, right, and the arrow is going up, you literally, so it's AY, right? You literally go up by that amount, right, when you're going left to right. So this is 0.6, and the shear force is in kilonewtons, okay? So we start at, it goes 0, jumps up immediately, there's a discontinuity at the point force, which is the support reaction. to 0.6, and then basically, since there's no other actions happening, like no distributed loads or anything, it goes across flat and gets to by, okay? Once it reaches by, we go up by by because it's a positive number, so we go up by a further 1.4, leaving us at 2. So 0.6 plus 1.4 is 2. So you can think of the supports like little jumps. I can draw an up arrow if I want. Right? And we follow across horizontally, and we jump down by 2. So we do that because there's a point load of 2. Whenever there's a point load, you jump down, generally because loads are acting down. You jump down by that amount. And if there's a support reaction that's positive, you jump up by that amount. So that makes sense, maybe? Yeah? So you can see where I kind of constructed this graph from. So this goes from 2 to 0, essentially, right? And that's our completed shear force diagram, right? If we go back to the original schematic, it looks like that, yeah? Okay. So the bending moment diagram is actually the integral of the shear force diagram, okay? But now there's a kicker because we have to incorporate the point moments as well. So the shear force diagram is unaffected by that point moment 1.6. However, the bending moment diagram, we do have to account for it, okay? So what I'm gonna do is I'm gonna literally break up my shape into 3 smaller shapes. In fact, 2 smaller shapes. So normally for a question like this that doesn't have a point moment right here, I would break this up into only like 2 rectangles, right? But what I've done is I've done it like this because you'll see that this point moment almost breaks up our beam further in the bending moment diagram. Okay? You'll see what I mean, hopefully. So you literally calculate the area of these. So remember that all of these are 0.5 meters. And these are in kilonewtons, right? So the area of 1 is that area of that rectangle, right? So that's 0.6 kilonewtons times 0.5 meters. So what units does that give us? Kilonewton meters, right? You see where this is going? Because since it's in kilonewton meters, this is going to give us kind of the values we need for our bending moment diagram, which will be in kilonewton meters, right? Okay, shape 2, it's 2 kilonewtons times 0.5 meters. Oh, sorry, I wrote kilometers. Oh. Yep, that gives us 1 kilonewton meter, right? Cool. So, how this plots onto a moment diagram is, okay, basically, this part of the shear force diagram is positive, right? And our moments are like gonna follow. How do I explain this? Okay, basically, I'll split the beams. Here's what it looks like. It slopes up slowly. So the bending moment starts at 0, right? And it slopes up, and the magnitude it reaches at that point is 1. The magnitude it reaches is what we calculated here. Right. And then here's something to remember. This is a positive point moment, but using left to right, like using our graphical method, this is going to result in a downward spike instead of an upward spike. It's a little bit counterintuitive, but it goes down like this. So a positive point moment will make us go down. Okay. So that's 0.3 kilonewton meters, right? So, but now we have to subtract off 1.6, which is our point moment, right? That's the point we're at now. Now it'll increase by another area of 1. Okay. Goes to here. So that goes to, it's negative. Negative 1.3 kilonewton meters. Now it's at negative 1 kilonewton. Far out. Keep changing colors. Okay. And now, maybe it's better if I draw it like this. And finally, we add on, from negative 1, we add on another 1. Okay, and that's the area of 2. So that goes to 0. So all of this area on this graph is positive bending, and all of this area is negative bending. Okay, that's our graphical method. Yeah, question.
I got lost after you said you're dipping down from from 0.3 all the way to negative 1.3. So
Oh yeah. So you can't see it on the shear force diagram because it's not due to a shear force.
yeah.
It spikes down because of our point moment. Yeah.
You said it spikes down, and then why did we go back to 1 again? Why did we
Oh,
go
right.
to negative 1?
Oh yeah. I see what you mean. So we added another rectangle of 1.
Oh.
That area is 0.3. So it goes from negative 1.3 back to negative 1. So it's over that area.
And then we add the 1 back up, so it's back to 0.
Because this area is bigger, the magnitude's bigger, and so it goes from negative 1 back to 0. Yep. Yeah, thank you. I didn't do the best explanation for that. If you guys have more questions, yeah.
Why is our force graph split to 3 parts, not like 4 or 5?
Force graph. Are you talking about the shear force graph here?
Yeah.
It's a good question. So I've basically split it up into the minimum amount, like the minimum amount of splits that's not redundant, I guess. You could split it up further. So say you split up this, but the idea is that I only care about the critical points on the bending moment graph. So since these follow a different slope, right? Because of the change being different, if that makes sense. So I've decided to split it up like that. Again, this is something that comes with a lot of, when you do practice questions, you'll get the hang of it pretty quickly. I've skipped a lot of steps in my explanation, and some of the derivations actually come from the algebraic method, which I'll explain further on. But the idea is this graphical method, even though it might not be intuitive right now because you guys are seeing it for the first time, this is actually the easier method to understand, and generally you grasp the concept quicker. I found when I teach this one first. So we don't really know why yet on why these things are the way they are, but we know what they'll look like, and we know the fast way of doing it. Do you know what I mean? Yeah. Are we okay to keep going? Yeah. Oh, the question also asks for what is the bending moment at point B, right? And point B is right here. It's negative 1. So the graph will tell you exactly what the internal moments are at every point along the graph. Very kind of elegantly, I guess. So that's the advantage of the bending moment diagram. It tells you what all the external forces are doing and how extreme they are. So if you wanted to find what the max bending moment was along the beam, you look at all your bending moment diagrams, and then you're like, okay, well the max moment is negative 1.3 because that's the highest magnitude moment along my beam, and you can design for that in structural engineering. Okay. Do you guys have any more questions right now? Okay. So here I've got another example. So this is like a beam. I've got a question. Is it a simply supported beam? you reckon it's a yes? Okay, so this is the you reckon it's a no?
Uniformly distributed.
Oh, the external actions, which are like the uniformly distributed, that doesn't affect whether it's simply supported or not. It's what the supports are. But with that said, it's actually not a simply supported beam, because a simply supported beam's definition is the supports are at both ends. So what we actually have is we have two different spans of the beam. So this is called a continuous beam now. So we have that regular part, and then this is called a cantilever span of this continuous beam. Yeah. Okay, so we draw the shear force diagram and moment diagrams, and we also have to determine the distance b where the bending moment is 0, right? Yeah, so how are we going to do this? Well, first we determine the support reactions. I've actually skipped this step because we've seen it in the last question. But it's the exact same thing. You do all your equations of equilibrium and you can find what those values are. So now we basically know this, this, and this, right? This is going to help with drawing our shear force diagram and all that. Okay. So now we have a shear force diagram, right? This is the meat of it, right? Because AY is 1.125. Is this going to go up or down from left to right along our shear force diagram? Yeah. So we go up by 1.125, right? Okay. Now, we haven't seen a uniformly distributed load act on a beam yet, right? So is this going to go horizontally like that? No, because essentially this distributed load is going to keep weighing down on the beam as you go further along it, right? What that means is that you're going to go down like this by a slope equals the distributed load, which is 1.5 kilonewtons per meter, right? Yep. Yeah. So on shear force diagram, if we have a reaction which acts up, right? We consider that as a shear force diagram, and the graph jumps up. And if we have a load, which generally they act downwards in the direction of gravity, that'll cause the graph to go down. I'll answer this once we get to the algebraic method. Yeah. It'll tie in what I was saying about internal forces better. Yeah. But for now, you just kind of accept it, and we'll roll with how to do the questions. The other thing about how the civil school runs this course, right, is that they actually don't care whether you use the graphical method or the algebraic method. And because the algebraic method's faster, generally you can get away with using the graphical method and still get full marks in a quiz. Do you know what I mean? So I'm teaching you the lazy way because it will still give you full marks, you know what I mean? Whereas the longer way, yeah, anyway. But in the finals, you might need to know the longer way. But in the midterm that's coming up in week 5, yeah, I would focus your efforts on learning the graphical method, to be honest. Okay, so we go down, right? And then the question is, what is this number here? Like, how far down have we gone, right? Well, the way you calculate this is your starting number, right? 1.125, and you have to subtract that distributed load, 1.5, multiplied by how far along we've gone. And we've gone along 2 meters. Yeah? So this number here is negative 1.875. Okay, next what happens is we have this roller support, and this support reaction will go upwards, right? By 3.375. Okay. So now this will jump from negative 1.875 up to 1.5. So all you do is you get this number and you add 3.375 to it. Yeah. And you find what that spikes up to. Okay. And then lastly, we just have the same distributed load, so the same slope that's acting downwards, yeah? I should probably draw it like this. And it caps off like that and finishes at 0, right? So this should make sense because we have our shear forces, our discontinuities at the point loads, including our support reactions. The rest of the beam is continuous in terms of its slope. Yeah. Okay. So, yeah.
Could you explain why it goes back to 0?
Oh, yep. Good point. So, the distributed load acts down at a slope of 1.5 kilometers per meter. Yeah, but I didn't explain that. That geometry just happened to be 1 meter. Yeah, but the idea is that so if you have a simply supported beam like this, right, you expect the shear force diagram to look something like this, right, where the support reactions is where the discontinuities are, but it still ends up being 0 on both these ends, right? So when you move that support in like that, right, you expect the shape to actually look like this. But it always finishes at 0 on either ends, regardless of if it's a discontinuity or not. Yeah. Okay, does anyone else? Yep, good question.
Is gravity negative because it's more force pushing in a clockwise direction, which is negative moments?
Oh.
Is that why it gets more negative?
So I don't want you to think about moments yet, because we're just analyzing the up-downness of the forces. That's the shear forces, right? Yeah. When we look at the bending moments, then you're thinking on the right track. Yeah. Okay. Here's the trick with the graphical method, yeah? So essentially, we know that this is positive, this is positive, this is negative, this is positive, right? Okay, easy. What I'm going to do is I'm going to find the area of all these. What's the problem with that? Well, when we split up this triangle, you're going to struggle to find what B is. That distance B is currently unknown, but there's a way to solve it using a technique called similar triangles. So I'll show you what that means. But firstly, just know that this geometry here is 2 meters, right? And we know that, let's just call that distance from the left support to where the shear force is 0. Let's call that B, right? This distance here, we know, has to be 2 minus B, because if the entire thing is 2 meters, you subtract B off, that distance has to be 2 over B. Okay, so if we have a triangle that looks like this, right? And a triangle that looks like this, right? We can compare their slopes. And because this is uniformly distributed load, right, they're going to have the same slope. So this is a bit of information we know about the unknowns, right? So we literally compare the rise and plug that in. So the rise is 1.125 here, and the run is B. So B is what I've called this distance here. And that's going to be equal to, down here, so actually what I like to do, the maths works out better actually if you don't put a negative here. Right. So we're just comparing the slopes of these triangles as if they were orientated that way. If that makes sense. Hopefully. Okay. I don't think that makes sense, but just you take the absolute value essentially of that magnitude. Okay. And we call that distance 2 over B. Does this part make sense so far? We can actually just use algebra now to solve for what B is, right? So we cross multiply. Right. get rid of the fraction. And you can see it's pretty trivial just to work out what b is when we solve it on a calculator. It's 0.75 meters. So 0.75 meters from the support on the left, that's where we're going to have zero shear force, right? Okay. Now we can label these triangles, right? And we can solve for those magnitudes for our bending moment diagram. Okay, so what's the area of that triangle? Well, this area of a triangle has to be half first, right? Half base times width, right? So b is the base times height, rather, right? So the base is 0.75 meters, and the height is 1.125, right? That's from over here on our graph. That results in 0.422 kilonewton meters, okay? For triangle 2, which is this one here, right? We do the same thing, so we make it half, but what I like to do is I like to include the negative here. You can do it in terms of magnitudes, but I always make mistakes. So if it's a negative triangle, include the triangle. Include the negative here when you're doing the calc. And our base is 2 minus b, right? So it's simply 2 minus 0.75 meters, okay? And our height is going to be this one. Yeah, technically you could have done the negative over here. That makes more sense in your head. But yeah. That one is negative 1.172 kilonewton meters. And finally we have our third triangle, which is probably the least problematic because these numbers are a lot nicer. So it's also half, right? The base, if we scroll up, the base is 1 meter. And the magnitude is 1.5. So this is a nice clean number. This one's 0.75 meters. So let me just highlight those. That's area 1, 2, 3. Okay. Does anyone have any questions about that? We're just gonna implement this and do the exact same thing. However, okay, so what do you think the shape of this bending moment diagram will be? Because before, right, we had a shear force diagram. If I scroll up, we had a shear force diagram which is made out of blocks, and the bending moment diagram was triangular, right? So if we have triangular shear force diagram, what is our bending moment diagram going to be? I'm hearing a few different answers. The answer is parabola shaped. So our shear force diagram will inform on our bending moment diagram the slope. Okay, so in areas of zero shear, that's where you're going to have a flat part of your parabola. Got it? So if we consider upwards as the positive direction, which in this course way prefers, in future courses it actually flips upside down. They'll explain why in future courses, but in this course we'll take positive moments upwards, so the intuitive way, right? Basically, if we start with a positive shear, right, we could start by going upwards like that. Sorry. Yeah. Okay. The slope of it, okay, does it look like this or does it look like this?
It's decreasing.
Exactly, it's decreasing, you're right. So it starts with a non-zero slope, right? It starts positive and then decreases eventually until it's flat, which is the area of zero shear, right? Or like the zone of zero shear. And it keeps negatively decreasing like this, right? And then it's going to have a sudden jump in continuity, right? It's discontinuous or whatever. And it's going to change directions entirely and do that. And decrease. And where the shear is zero, like if it slowly goes towards zero, it slowly becomes flat again like here. So it's flat here and it's flat here. Okay, got it? This is probably confusing the first time you see it, Again, a lot of practice will make this relatively intuitive. Yeah. Sorry, could you say that again? It's actually okay. Well, here's the thing, right? Once we do all these calcs and add them up properly, it will be 0. But assuming there's no point moments, your bending moment diagram is actually continuous the entire time, firstly. So there's no like sudden jumps here. That's the first thing you need to know. And the other thing you need to know is that the start and ends will always be 0. Same with the shear force. So the leftmost one and the rightmost one will start and end at 0, and the bending moment starts and ends at 0 as well. Okay, let's figure out these numbers. So this number here, at b distance away, so we go 0.75 meters, right, is going to be equal to area 1, right? So that's 0.422, right? The next one here is going to be 1 plus 2, right, which is 0.422 minus 1.172, okay? That's negative 0.75. And finally, 1 plus 2 plus 3, because this is negative 0.75, you'll see that when you add on 0.75, that just nets to be 0, right? It's equal to 0. Okay. Does anyone have any questions about these methods? Okay, so we're going to keep going. And it's only going to get harder, right? So if you have questions, you should ask now, I guess. The algebraic method is slightly harder, that's all. But okay. You know what? I'm just going to keep going. So question 3 here. What type of distributed load is this? Triangular. Okay. So I'm going to use this to illustrate our other method, which is the algebraic method, and where all the derivations come from, and why I've been yapping on about the left-hand notation for internal forces and stuff. So the first step is we find all of our reactions, right? That part's straightforward enough, right? The only thing you really have to consider is that to find this distributed load, you find the area of that triangle, right? And for the moments part, the location of it will matter, right? So here I've done some of the moments about B. So that distance there will be 1 meter, right? Because it's 1/3 of the length from the big side. Yeah. So that's what I've done here. That's basically that triangular distributed load. Okay. Next, here's the notation. Okay. So what I'm going to do is I'm going to cut. So we call these nodes, right, along a beam. We've been calling them points. We can call them nodes. So the point on the left of this beam is called point A, or node A, and the point on the right is called node B, right? So when we make a cut, it has to refer to 2 nodes. So we cut AB, right? So that's also called member AB, right? If we cut along it, right, we draw it like this, essentially. And what we're going to do, firstly, 0.75 is the reaction at A. That doesn't change anymore, right? What happens is we need to create a function for shear force and for bending moment, right? With a varying distance x. So that's what I've drawn along here. I've drawn a kind of coordinate system for what x is. So over here, x is equal to 0, right? And as x moves along, yeah, etc., right? So if I scroll back up quickly, you know how I was talking about these internal forces in a beam? is where it's actually going to kind of matter. So we're basically just drawing this, but down there. This is our cut, right? That's what we call the cut. And I've exposed a bunch of the internal forces. I haven't actually drawn the axial force arrow. It still exists, but why do you reckon I haven't drawn it? Yeah, right.
The actual force is 0.
Yes.
And it doesn't apply to the shear force diagram.
Very good. So there's something called an axial force diagram, which will be relevant for frames, and it will also be relevant technically for trusses, because trusses will take on axial forces. But for beams, it's not critical. At least in this course, I want to say. So I don't care about the axial forces, essentially, that's what I'm saying, right? I only care about the shear forces and the internal moment, right? Because this is going to inform our functions for our shear force diagram and bending moment diagram, right? Okay. So what we know for a fact is we know the slope. So over here, we have a rise of 1.5, right? And we have a run of 3 meters. So we actually know what the slope is. That's 0.5, right? Oh, one thing I should note is for this question, you have to use the algebraic method. You can't solve this anymore, and I'll explain why at the end. You can't solve this anymore using the graphical method. So as soon as you see a triangularly distributed load, you have to launch into the algebraic method and do it the long way like this. Okay, next, we can find what this varying distance is. I might draw it in purple actually. So what I'm trying to represent is I want to find the magnitude as it's moving along the beam. So what this means is the slope multiplied by the run. That's how you get that that magnitude essentially, right? So that is 0.5, which is our slope that we found, multiplied by x. That's our slope multiplied by our run, right? Okay, cool. Now what we have to do is we have to take the equilibrium, right? The vertical equilibrium, but account for our shear force, right? Because our moment we can treat almost like a point moment. That's not going to be included when we take the sum of the moments, right? So we take the sum of the moments including this downwards v shear force, right? So it's going to be negative because it's acting down, right? In this convention. And now we look at the vertical support reaction. So we add on 0.75, right? Lastly, we care about this triangle, right? The magnitude of this triangle, right? And it's going to vary with x, okay? So the magnitude of this triangle, okay, firstly, let's keep it simple. The area of a triangle is half base times height, right? And we know that these arrows are acting downwards. And since we're taking the sum of the forces with the positive direction going up, we know that this value has to be negative. Got it? So half, the base is going to be x. Base is simply x, okay? And the height is going to be 0.5x. That's the slope multiplied by the run, or the base again. Okay. Yeah, following? So that's how we get this shear force. So we rearrange for V. And these x's actually multiplied together, and this is what I'm talking about. If you have basically, if you have a triangularly distributed load on your free body diagram, when that gets moved across into a shear force diagram, it's going to become a parabola. When that gets moved across to a bending moment diagram, it's going to become a cubic. That's why it's very difficult to do using the graphical method, because graphing a cubic is quite difficult, right? Without knowing the exact function of it. Okay. X is equal to... Okay, I think I'll leave it at that for now. And then, so I'm going to highlight that. This is our function, a generalized function for shear force. Next, we're going to analyze the bending moments, right? So, this moment is acting at the cut, and we pretend it's like almost like a point moment, right? And it's going counterclockwise, so it's going to have a positive moment. This, this reaction, right, that's going upwards, is causing a negative spin about the cut, right? So we're taking the sum of the forces about the cut. So it's going to be negative, and it's going to be 0.75 times the lever arm, which is x. Yeah, you got a question? Oh, yeah. So we're analyzing this triangle, and we know that the magnitude is going downwards, right? So we take half base times height. The slope just affects what that height of that triangle is for a varying distance. Yeah. This triangularly distributed load is acting straight down, but sorry. Sorry, say that again. Oh yeah, V is the internal shear force. Yep. So we're graphing. I think it'll make more sense when these functions move on to the shear force and bending moment diagrams, man. Yep. Okay. So bear with me, guys. So we're at sum of the moments about the cut is equal to this, right? Which is the internal moment minus 0.75 x. So that's that times the lever arm of x, right? Next, we have to do this triangle, right? And it's 2/3 along the length, right? So we have to do this. So the magnitude, okay, that's the magnitude. I'm literally just going to copy the magnitude over, right? Because we're looking at this triangularly distributed load, and that's our magnitude, right? It's multiplied by, okay. Sorry, 1 second. Okay. Let me think of how to explain this. So we're analyzing some of the moments about this cut here, right? And we actually already have the magnitude from the shear force calculation. What is this lever arm? X on 3, very good. So all we have to do is multiply this by x on 3. That's our lever arm. And it causes a positive moment, so it's a plus, right? If I rearrange for m, right, we get this 1/12 x cubed. So we have a cubic bending moment function, right? Okay, let's map these out on the bending moment diagram, and the shear force diagram, right? Okay, so as we've said, we start with, like, this is why it helps to learn the graphical method first, because you'll know how these support reactions kind of work when you're graphing it, right? This will jump up by the reaction AY, which is 0.75, right? And now we can graph it. Yep, did you have a question? Sorry, what do you mean? these questions, and then I'll talk to you after class about that. Okay. Okay, so what shape do you reckon the shear force diagram will take on if it starts at 0.75? Remember, this was the function to graph it. Anyone? It's parabola. Very good. And so we actually have a lot of information just by looking at this function. Firstly, the y-intercept. That's kind of, if this gives you like any kind of flashbacks to maths, this is the y-intercept. And then we have a negative x squared, which indicates kind of sad face parabola, right? So it'll look like this. Okay. Okay, one thing to note is we know what by is. By is 1.5. And so we know that this will end on 1.5, negative 1.5. And then jump to 0 because of our understanding of the shear force diagram, right? So the question is, right, actually, what I'll do is, what we've done is we've graphed the shear force diagram. I'll graph the bending moment diagram, and then I'll discuss this distance here. Let's call that B, right? Because in the graphical method, when you get up to the stage, it's very difficult to find out what B is, right? Because it's a function of some parabola, right? Okay, so moments will be start and end at 0 and be continuous, right? So our shape, it's still a cubic, keep in mind, but it will actually look like this. Right? So it's kind of like a wonky looking parabola where the middle isn't quite the apex, right? So again, it will actually look like this. And this will line up with our location B for where our max moment is. Okay. So basically we're graphing this. Far out. Okay, what I might do is I'll solve for B. Okay, so over here, right? We're looking for the value of x that causes a shear force of 0, right? So we do 0 is equal to this minus this, and we're solving for this value of x, right? Because we're looking for what this value for b is, right? You rearrange it. You can find it quite easily since we already have the functions, right? So x is equal to 1.732, right? So that is 1.732, right? Now, what we can do to find this max moment, right? All we have to do is plug in this value into our equation. So this is a function of x, right? Mx is equal to all that stuff. What we're doing is we're plugging in this value of x. And that's just a matter of whenever you see an x, you chuck in that, right? And it's cubed for that part. That will give us that the max moment is 0.866 kilonewton meters, right? Okay. Yeah, so that's the algebraic method, yeah? Yeah, you got a question?
In our civil workshops, when we tried the first two questions, they had a point where we didn't deal with x's, but in this example, we're dealing with that we are considering that a distance from a certain point to a certain point where we cut is x. So when do we know when to decipher? Like when do we use a number versus when do we use x?
Oh, so x will represent a variable distance. So if you're solving for a function like this, you need to keep it generic. You need to keep it as a variable distance. And then what I've done is to solve for all this stuff, I've like for example, I wanted to find the moment at 1.732. So I've plugged in this value into that function, which is generic. Hopefully that answers your question. I'm not quite sure what you're asking, sir.
Like in some of our workshop questions, like the first two, they gave us to find at a certain point. So we did not really use x when we derive the formula.
Right.
While here we're using x. So
Yep.
I'm just confused which approach to use when.
Yep. Okay. Yep. Good question. So basically, I think I know what you're asking. So you're asking, when do we need to solve it with a variable distance x, and when do we need to be like find the moment at b or yeah. So we're doing it the long way, which is the generic way, which can solve for any point, not just the moment at b. That's also the one that's going to help us graph the bending moment diagram, because we're deriving the entire function. It's incredibly flexible. You can plug in a bunch of different numbers, output a bunch of different numbers, stuff like that. For the exact point b, the difference in the method is like, let's call this point 2/3 along C, right? We would do the same thing kind of with a cut. Okay. Sorry, I'm going to add a page here. Let me just redraw it, right? So say we want the bending moment, right? Like the internal bending moment at point C. The difference is, instead of calling this distance x, we're going to call this 2 meters.
Oh, so we have a random number instead of x.
Yeah, you have a fixed distance now.
Okay.
So it's not a variable distance. And you do the same thing. You just solve, you take the bending moments about point C, which is still the cut.
Yeah.
And you'll get the right answer. But it'll only give you one answer instead of a function which you can plug any number into. Do you know what I mean? Does anyone else have any questions with this method? Sorry, this workshop's gone a little rogue in terms of my flow and pace. I'm just going to run through this next one theoretically because it's going to take a while and run us over time. So this last question here, right? We have quite a difficult looking question. So there's a point load, there's a triangular load, there's a point moment, and these things, right, which are called smooth truss bearers and smooth journal bearers, right? These, again, are mathematically the same as pin supports and roller supports, right? So this one holds the rod at one end and lets it, it's basically a pin support, but lets it rotate and stuff. Whereas the journal bearer lets the rod slide through, so it kind of acts like a roller support, essentially, right? Essentially, this question, like, it's a good one to practice. I've got all the solutions up on my notes, so when you go home and potentially practice this, because there's a lot of different types of loading on it, but you're gonna run into kind of a problem, right? So if you cut left to right, say we do cut AB, right, and go that way, right, that's gonna be fine. But then if we go cut BC, right, and we call X going that way, what type of loading is that? That's a trapezium now, right? And trapeziums, we know, are much more difficult to deal with than triangles. There's a way you can solve it. That's to divide it into a rectangle and a triangle. But again, then it's like you split it into two loads, and it's just annoying, right? The other way you can do it, which I've done here, is go right to left. If you go right to left, now it's a triangle, right? So you save yourself a lot of work by doing it like that. So I'll kind of run you through the solutions as we do this. But what I've done is I've actually decided to do the left part in the graphical method and the right part in the algebraic method. So you can actually mix and match if you like. So the other thing to note, is that true? No, that's not true. Okay, this is what I mean by like my mistakes will have a lot of, my notes will have a lot of mistakes. Yep, support reactions, and I straight up haven't even done the graphical method calcs until below because it requires so much less working. So what I've done is I've done the triangle but right to left. Same thing, slope, which allows you to work out that vertical part of the vertical magnitude. You get a function for v and you get a function for m, right? And then you actually graph right to left as well. So whenever x is 0, it's the rightmost part, and then increasing goes that way, right? Yeah, and I mean, I did this just to show it off, but you can use integration when you're doing this whole like finding the magnitude if you have the function already, right? But yeah, the graphical method, this part of the beam here, right? You can do just using the graphical method. So it looks like that. And yeah, that's that. Okay, lastly, I want to show off machines and frames, okay? So I know I've talked to you guys a lot so far. Let me give you the context first. Okay, basically, how it works in the civil school, term 2, 1300, is that you technically don't need to learn about machines, but you do need to learn about frames. Mathematically, they're very similar. They rely on something called hinges. So hinges are like a pinned joint, right? You'll see this pop up next week when we're looking at trusses as well, but they have this pinned joint, and this gives you additional information to solve it. So yeah, here we have sorry, one sec. So these are two pin supports, right? And if you think about the lines of action, right, these don't line up, essentially. If you take the sum of the moments as is, you're going to run into problems because you're going to have two unknowns, right? It's going to be difficult to solve. The trick is that at the hinge, you can split up a machine or a frame with a hinge by the hinge. Hinges will give you additional information, and then you can solve simultaneously, basically. So here I've drawn this part of the machine and this part of the machine separately, right? That's this part and this part. And again, it's split up by this hinge. This hinge has like a support reaction acting at the joint, but it's equal and opposite, right? So I've called it CXCY because again, it acts very similar to a pinned support, but it's a joint, so it's not fixed in place. It can move around like that, right? And on the other end of your, where you're splitting it up, you just have to make sure these reactions are equal and opposite. And when you solve using your equations of equilibrium, you'll get these kind of things like simultaneous equations. You can solve them like that. Yeah. So with machines, right, we care about the support reactions. They're basically like hard, kind of like hard structures to solve, but we don't care about the bending moment diagrams or the shear force diagrams like we do for a beam, right? It's just finding the support reactions are actually quite difficult by themselves for these kind of things. But I think in like the finals, you might see some frames where you might need to graph the bending moment or shear force diagrams for. So you will have to learn this hinge method eventually. It's just this part of the course is quite condensed. It's going to feel like it goes by very quickly, and so I'm not going to have time until week 10 to explain to you how to graph the bending moment diagram for a frame. A frame looks like this, by the way. It's got columns and beams, and the bending moment diagram can wrap around like that, for example. Yeah. So that's as hard as it gets for statics in this course, basically. But I'm just warning you ahead of time. If you want to learn about how hinges work properly, I've given you an example there. Okay, that concludes my class. You had a question, right? You feel free to come to the front. I can run it through with you. But otherwise, yeah, you're free to go.